Alright guys, so the best way to learn how to graph logarithms is to go back and review graphing exponential growth and decay functions. So right here we have an exponential decay function, and like always the first step is to identify h and k. So your h value is what? Positive 3, and your k value is what? So the h we know is positive 3, which means it goes in the positive 3 direction, 3 units to the positive side, and negative 5 for k means that it's going 5 units in the negative side, which means 5 units down. So anytime you identify it, or after identifying h and k, we ignore h and k just for a little while. I like to box it in. You don't have to do this, but I like to box it in. That way I could just focus in on this part, and I don't even have to look at h and k, right? So if I wanted to graph this, it's really easy. All I need to do is make an XY table. XY. And let's plug in consecutive integer inputs, negative 3, negative 2, negative 1, 0, 1, 2, 3. And what I like to do is simply plug in an easy input like 0. If you plug in 0 right in here, 1/2 to the 0 power, anything to the 0 power is 1. So one coordinate is 0, 1. And then what we could do from here, instead of plugging it into the function, we could simply understand that this is a decay function because it's less than 1 right here. The base is less than 1. And not only that, it's going to decay by that value 1/2. So the output 1 is going to decay by 1/2. So if I were to multiply this by 1/2, I will get 1/2. And if I decay 1/2 by half again, that means I multiply it by half again, that would be 1/4. And if I decay 1/4 again by half, that's 1/4 times half, which is 1/8. And the next one would be 1/16, 1 over 32, 1 over 64. And we know that it keeps getting infinitely smaller, but never actually getting to 0. It just keeps getting closer and closer to 0, but never actually touching. Now, if it's decaying going this way by half, going backwards, it wouldn't be multiplying by half, it'd be dividing by half, which is really multiplying by 2. In other words, instead of decaying by half, it'd be doubling, it'd be growing by doubling. So up here, you would have 2, 4, 8. And those are all the coordinates that we need to graph this exponential decay function. If you didn't want to do that, you could always actually plug in the input negative 3 into x, 1/2 to the negative 3 power. You'd have to flip it. 2 to the 3rd power is 8. So you could go through the actual math to get those outputs based on those inputs. But it's easier to just do one input, one output, and then make that output grow or decay depending on your base. Anyway, we have the coordinates. Let's graph the coordinates. That's 0, 1, which is right here. And then we have negative 1, 2, which is right here. And then we have negative 2, 4, which is right here. And we have negative 3, 8, way up here. Okay? So as we could see, from left to right, it's definitely decaying. It's going down. Maybe I shouldn't have drawn this, but because we still need to do an h and k shift. But that's okay. We could put some x's on it to show that this is not our final graph. Anyway, let's continue graphing the coordinates 1 and half, and then 2 and 1/4, and 3 and 1/8. Let me get closer to the graph so we could see this. So if here's the origin, if I go 1 and then half, it'd be right there in the middle, right here. And then the next one is the coordinate 2 and 1/4, which is really half of a half, which is even closer. And then the next one's 1/8, which is half of that. And then closer, half of that, half of that. At that point, it looks like it's touching. So I'm actually going to draw it like if it's actually touching, right? But we know it never actually touches, just infinitely approaches. Now, if you happen to draw this as your answer on a quiz or test, I'd give you half credit because you didn't do the h and k shift, right? Arrow here, arrow there. However, you need to do an h and k shift. So the h shift is 3 to the right and then 5 down, okay? So if you take all of these coordinates, 3 to the right and 5 down, start with this guy, you go 1, 2, 3, and then 1, 2, 3, 4, 5, right there. And then the next one, 1, 2, 3 to the right, 5 down, 1, 2, 3, 4, 5 right there. And this next one, 3 to the right, actually I already did that one. This next one, 3 to the right and 5 down. That would be 1, 2, 3. Did I do that right? One, two, three, 1, 2, 3, 4, 5. And you know, it gets kind of confusing with the dots. I recommend go to your asymptote. This one for sure, you know, it infinitely approaches this line. So if you need to shift this line 3 to the right, it's still going to be this line anyway. But if you go 5 down, you'll be at 1, 2, 3, 4, 5. So here's your new asymptote. Let's draw it right there. 1, 2, 3, 4, 5, right there. And we're drawing it like if it's actually on the line, even though we know it never actually touches, just infinitely approaches. So at this point, we see this dot up here coming down to this dot, coming down to this dot. And let's do a couple more. So since this one went 3 to the right and 5 down, you see this next dot, which is just 1 unit diagonally from it? You could actually find that coordinate by just going that same pattern right there. And we know that it goes half, and then 1/4, and then 1/8, and that's how it looks like it infinitely touches. So there's your final graph, the red one, not the blue one. So go ahead and put like some X's on that blue one, so we won't make, or so I don't make the mistake of counting that one as your final graph. The red one's your final graph. So it does take a while, especially when you explain everything, like I just did on that one. Let's talk domain and range. The domain of the red line, of the red curve, I should say. We're talking about X values for domain. Now, does this red line go to the right forever? Yes, it does. It goes to the right forever. So it does have all the positives on X. Does it go to the left forever? It looks like it doesn't. It looks like it curves straight up. But we know it doesn't ever just go straight up, right? It doesn't approach an asymptote. It still continues to grow to the left, slowly but surely. So if you were to take this paper and you keep growing, you'll still see that it keeps going to the left. So it really does go to the left and to the right forever. So the domain is X equals all real numbers. Now how about the range? The range are your Y values. And we clearly know that it goes up forever, but it doesn't go down forever. It actually stops right here at this line right here. And what is this line right here? Y equals what? What is that line? What is this line right here? That the red line infinitely approaches but never actually passes? Y equals -5, guys. Right? Your K value. So Y equals -5 is that line. So we know that it never goes below the Y equals -5 line. It infinitely approaches it but never actually goes below it. So the range value, you would say it's all your Y values that are above -5. That would be greater than -5. So that's a review of exponential decay. Let's jump to a logarithmic function. Now this one has log base half of x. Now if I asked you to find the inverse of y equals log base half of x, if I asked you to find the inverse, what would you do? You would switch x and y. You would say x equals log base half of y, and then you'd have to solve for y, and the problem is you have a log base half right there. So you want to get rid of the log base half. To get rid of a log, you'd have to undo it by doing the inverse operation of a log, and the inverse operation of a log is raising it to be the power of the base that you have on the log. So you would have to take this whole right side and raise it to be the power of base half. And what you do to one side, you do to the other side, you'd raise the x to be the power of base half, and the equal sign now comes between the bases. So it's no longer up here. What does this really say now? It says 1/2 to the x power equals 1/2 to the log base 1/2 of y. And the 1/2 to the log base 1/2, that cancels out, and you'll get y equals 1/2 to the x power. Okay? Do we understand that? Okay, so if I ask you to find the inverse, we end up with the exponential decay function that we see there. Now, take a look at that inverse. It says y equals 1/2 to the x power. So I just found the inverse of this guy. And what is the inverse? It's y equals 1/2 to the x. So if you take your hand and cover up the word log, it actually shows you that. It shows you y equals the base 1/2 to the x. So in other words, the inverse of that is simply y equals 1/2 to the x. Now you could find the inverse the way we did over here, or you could just cover up log and that'll be your inverse right there, okay? Obviously covering up log is a lot faster, so when you cover up the log, you'll have y equals base 1/2 to the x, and that's an exponential decay function. Now, to find those coordinates, that's easy. Just do the consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3. And as a matter of fact, if we zoom out, we see that we already did the xy coordinates for y equals 1/2 to the x power, and we got these coordinates, right? So we already know the answers to this guy. I'm just going to copy them over again. That's the 1, 1/2, 1/4, 1/8. That's 2, 4, 8. Now those are the coordinates to the inverse. These are the coordinates to the inverse. Now we don't want the coordinates to the inverse. We want the coordinates to the logarithmic function y equals log base 1/2 of x. Now if we know the coordinates to the inverse of this original one, then we really do know the coordinates of the original one. Why? Because to find the inverse, if you had coordinates, all you do is switch the x's and y's. That's all you do. Like, pretend I didn't even give you the equations. I just gave you the coordinates, and I told you, find the inverse coordinates. What are you going to do? You're going to switch x and y. So your new coordinates, instead of -3 and 8, it's going to be 8 and -3. 8 and -3. Instead of -2 and 4, it's going to be 4 and -2. Instead of -1 and 2, it's going to be 2 and -1. Instead of 0 and 1, it's going to be 1 and 0. Instead of 1 1/2, it's going to be 1/2 and 1. Instead of 2 and 1/4, it's going to be 1/4 and 2. And then 1/8 and 3. Okay, so I hope we all see that. And now we have our real coordinates to the logarithmic function, and we could actually graph it. So let's graph 8 and -3. 8 and 1, 2, 3, it's right here. 8 and -3. If we go to 4, -2, 1, 2, 3, 4, -2 is right here. If we go to 2, -1, 1, 2, -1, it's right there. If we go to 1, 0, 1, 0 is right there. If we go to this coordinate, this is where it gets a little interesting. 1/2 and 1, halfway on the x. So you're at the origin. If you go halfway on the x and then 1 up, you'll be at that halfway point right there. So right there, halfway. And then it says 1/4 on the x and 2 up. So it gets even closer to the y-axis, closer to the y-axis, closer to the y-axis, till you just start drawing it like if it actually is on the y-axis, even though you know it never actually touches, just infinitely approaches. Now let me ask you this, guys. Did we have an original h and k on this logarithmic function? No, so we're done, right? The only difference is if we did have a h and k, all we'd have to do is take these coordinates and shift them according to h and k. But since we don't, we're done. This is it. I mean, this is our logarithmic like that. We're done. Asymptote. Talk domain and range. The domain, x equals, is it all real numbers? Does any part of this graph right here, does it go to the negatives on the x? Never. It infinitely approaches the x value of 0. So we know that it's all above the x value of 0. It's all to the right of it. So it's not x equals, it's actually x has to be greater than, that's disgusting. X has to be greater than 0. Now the range is y is all real numbers because it really does go up and down forever.